Hello, I'm going to be working through problem set 9-7. Wow, that is too thick. Question 1, I'm flipping a coin 3 times. What is the probability of getting exactly one head? Okay, so to get exactly one head, it could either be head, tail, tail. Could also be tail, head, tail. Sorry. Yeah, tail, head, tail, or tail, tail, head. So those are the total number of desired outcomes. That's 3 factorial over 2 factorial. Um, 3 factorial divided by 2 factorial, because this is essentially the number of ways to order the word HTT, and T is duplicated, so that's going to be double counted. You can also think of it like this. This is also 3 choose 1. We're basically we have 3 spots, and we're trying to choose one spot for the head, and that's why it's 3 choose 1. But whatever you do, you should be getting 3 total desired outcomes. And of course, we have 2 cubed equals 8 total outcomes. So the answer is going to be 3 over 8 for exactly one head. Part B, what is the probability of getting a head on the first toss? That's 1/2. Kind of a trick question, right? The fact that you're flipping it 3 times doesn't matter. The probability of getting a head on the first toss is 1/2. You can think about it more explicitly. The number of desired outcomes is 4 because it could be head. The first one has to be head, but the second one can be either head or tails. So it's 2 squared over 2 cubed, which is 4/8. Part C, what is the probability of getting at least 2 heads? That is going to be the probability of getting 2 heads plus the probability of getting 3 heads. So probability 2 heads, you will find that to be equal to 3/8. Do the math. And then the probability of 3 heads will be 1/8. And so the total is at least 2 heads. The total will be half. Next question. I'm drawing a card at random from a standard 52 card deck. What is the probability of getting a face card? Um, there are 12 face cards. Alternatively, you can think about the fact that, there are um, 3 face card ranks, Jack, Queen, King, and there are 13 total ranks. So this is 3 over 13, or 12 over 52. What is the probability of getting a red card? It's going to be 1/2 because 2 out of the 4 suits are red, the diamond and the heart. Part C, what is the probability of a red face card? It's going to be 3 over 26. Um, why is that? That's because there are 2 red cards per rank, because half the suits are red. And so there are going to be 6 total red face cards. That'll be 6 over 52 plus 3 over 20, which is equal to 3 over 26. Question 2, we're going to leave our answers, sorry, question 3, we're going to leave our answers unsimplified. If I draw 2 cards at random, what is the probability of getting 2 aces? So I'll show you guys both methods. First is the probability multiplication. Second is the more typical desired outcomes method. Okay, I'm drawing 2 cards at random without replacement. I should have specified that. You can always assume that it's without replacement. 2 cards at random. What is the probability of getting 2 aces? The first one is going to be 4/52. I'm just not going to write the lines anymore. The first card, we have a probability of 4/52 because we have 4 aces and 52 cards. And then there are going to be 3 aces remaining and 51 cards left in the deck. That's the answer to the first part. You could have also asked yourself, how many possible 2-card hands are there with 2 aces? And the answer for that would be 4 times 3 divided by 2 factorial. And then you could have divided that by the number of total 2-card hands, which is 52 times 51 divided by 2 factorial. So that's the same thing. Question B, if I draw 2 cards at random, what is probably getting a pair? For this one, the first card doesn't matter because all I need to do is make sure that the second card matches the rank. So in order to match the rank, I'm going to have a probability of 3/51, right? Because um, 1 card from that rank has already been taken, so I have 3 left out of 51 cards. This is the same as if we counted all the 2-card hands with pairs. That would be 52 times 3 over 2 factorial. And the total number of 2-card hands is 52 times 51 divided by 2 factorial. So that gives us the same thing. For C, if I draw 3 cards at random, what is the probability of getting a triple? First card doesn't matter. Could be 1. So probability 1 for the first card. Second card, I want to match the rank. So 3/51. Third card, 2 left, 50 cards left. That's my answer. How many 3-card hands have triples? That would be this. And how many total 3-card hands are there? It's going to be that. So we get the same thing. Question D. If I draw 5 cards at random, what is the probability of getting a flush? This was on the classwork, wasn't it? First card doesn't matter. It can be any suit. So remember, a flush is a 5-card hand with all the same suits. So first card doesn't matter. It could be anything. Second card, I'm going to want to match the suit, and I'll have 12 suits, 12 cards of the same suit remaining. I have 51 cards. Then I'll have 11 of that remaining, and 10, and 9. And you get the idea. Part E, if I draw 2 cards at random, what is the probability of getting 2 different suits? Once again, the first card doesn't matter. Second card, I want to make sure I'm not getting the same suit. And there are 39 of those remaining out of 51 cards. Why 39? That is because I have 3 suits remaining to choose from, and there are 13 cards left from each of those suits. So 39. All right. As promised, I'm also going to work on the last page of the classwork. For those of you who didn't get it, these are all the poker hands, right? Okay. Now, these are quite a bit harder than what we just did on the problem set. And the reason why is for most of these, we can't use the same method of just multiplying the probabilities. You might think you could. So for example, for this first question, if I draw 5 cards at random, what is the probability of only getting a pair? I might think, oh, first card doesn't matter. Then second card, I want to match the rank. So it would be 3 over 51. Third card, I want to make sure I'm getting a different rank. And so I would have 48 cards out of 50. Then I want to get another different rank, 44 out of 49, 40 out of 48. Okay, this is wrong. The reason why this will give you the wrong probability is because you are requiring that the pair occur within the first 2 cards, when in reality, the pair could be anywhere within the 5 cards. For example, I could not only have ace, ace, 2, 3, 4, but I could also have ace, 2, 3, 4, ace, right? That's also a pair. And I'm not accounting for that within this current way of doing things. So this will not work. Now, you could have corrected for that, but I think an easier way is just to figure out the total number of desired outcomes over the total number of possible outcomes. So we're going to ask ourselves, what is the total number of 5-card hands with only a pair, nothing else? Okay, so this is the same question as last time. Let's say that we want the pair, let's say that we require the pair to be here. I'm going to have 52 possibilities for the first card and 3 possibilities for the second card to match the rank. Then for the third card, I'll have 48 possibilities because I want to make sure I don't get the same rank. 44 possibilities for the fourth because I want to make sure I don't get the same rank as the first 3 cards. I have 40 for the next one. And then I also need to account for overcounting. And I'm going to overcount within the first 2 cards and also within the last 3 cards. So I overcount by 2 factorial times 3 factorial. So that's going to be my numerator. 52 times 3 times 48 times 44 times 40 over 2 factorial, 3 factorial. And this is all over the total number of 5-card hands without order mattering, which is 52 times 51 times 50 times 49 times 48 divided by 5 factorial to account for the order not mattering. Okay, and so that will be my answer. And you can notice that this is different than what we previously calculated. And it's different because of these denominators, 2 factorial, 3 factorial, and 5 factorial. You might also notice that actually this answer is 5 choose 2 times the previous answer that we did when we did it the wrong way. And you can think about why that is. Second question is very similar. What is the probability of getting a 3 of a kind? Remember that having a 3 kind means you do not have a 4 of a kind. And it also means that you do not have a full house. So we want to make sure we're not getting a pair in the last 2 cards either. Let's say the triple is in the first 3 cards. 52 choices for the first card, 3 for the second, 2 for the third. And then we'll have 48 for the fourth card. And we want to make sure that these do not form a pair because that would be a full house and not a 3 of a kind. So we have 44 for the fifth card. Here we're going to be overcounting by 3 factorial within the triple and 2 factorial within the last 2 cards. My numerator, now 52 times 3 times 2 times 48 times 44 over 2 factorial, 3 factorial, over the same denominator, because I have the same number of total hands, right? Third question. This one is challenging. I've revised it a little bit from the classwork because I did not include the fact that a straight can actually be ace low. I thought the lowest was too low, but I actually looked at the rules again. It's actually ace low to 10 low. So 5 high to ace high. Okay, so how do we count the total number of 5 card hands that contain a straight? This one's pretty tricky and it's a lot different from the other way. First, we have to count the number of straights, only considering the ranks. So straights will go from ace 2, 3, 4, 5, 2, 3, 4, 5, 6, all the way down to 10, jack, queen, king, ace. And so we have 10 of these in total. However, once we consider each one of these straights individually, now we can ask ourselves, how many of those are there, accounting for suits now? And the answer is that there are 4 to the 5th of each straight, right? Consider the ace, 2, 3, 4, 5. The ace could be a club, diamond, heart, spade. So we have 4 choices for the suit on the ace. The 2 could also be a club, diamond, heart, spade. We have another 4 choices, etc. And so the total number of straights is 10 times 4 to the 5th. And then notice that in this case, I'm actually not going to be overcounting at all. The reason is because I've already limited the order of the straight. And so I'm not going to be overcounting because any new suit combination on the straight produces an entirely new hand. Plus, if you corrected for overcounting by dividing by 5 factorial, you wouldn't even get a full number. So it's pretty obvious that it doesn't work. Now we're going to divide by the same number of total hands to get the probability. If I draw 5 cards at random, what is the probability of getting a flush? I already did this. I already did this on a previous question. This is 1 times 12 over 51, 11 over 50, 10 over 49, 9 over 48. Yeah. If I draw 5 cards at random, what is the probability of getting a full house? This one's very similar to part F, right? Full house is a triple and a pair. Let's say that the first 3 are the triple and the last 2 are the pair. We'll have 52 choices for the first card, 3 cards for the second, 2 for the third, 48 for the fourth, and 3 for the fifth because I want to match the rank of the fourth card. So accounting for overcounting, 3 factorial, 2 factorial, that'll be 52 times 3 times 2 times 48 times 3 over 3 factorial times 2 factorial over 52 times 51 times 50 times 49 times 48 over 5 factorial. Same denominator. What is the probability of getting a 4 of a kind? Once again, let me limit my 4 of a kind to be the first 4 cards. I'll have 52 choices for the first card, 3 choices for the second, 2 for the third, and 1 for the fourth. Okay, and then for the fifth card, obviously it has to be something else. It's what we call the kicker in poker. Um, and there are 48 choices. It could just be any random card. Here, I'm only going to be overcounting within the 4 of a kind. So I'll be overcounting by 4 factorial. hope that's helpful. I know it's pretty hard, but it's also fun, isn't it? From a certain perspective.